Okay, in this lecture, we're going to talk about temperature, the difference between temperature and heat, do some conversions across the different temperature scales, and talk about specific heat. And I gotta warn you, temperature and heat is probably one of the most confused concepts in all of chemistry. It's intuitive, we think we understand temperature and heat, but we don't really have a molecular level understanding of what they really mean. So that's what we're gonna try to accomplish in this lecture. So again, let's start out. Even though we know what these terms are, we can define them explicitly, and this is an important one, right? Temperature, measuring the average kinetic energy of individual particles and motion. So even in the room you're sitting in right now, all around you, there are these microscopic molecules that are zipping around the room. Now, what you might not realize is that some of them are going very, very fast. Some of them are just kind of meandering and going slow, and some of them are going, I don't know, some medium speed. So there's a distribution of energy. The temperature is an average of all of those molecular motions. And whether it's the motion moving left to right in space, whether it's a molecule like this that is rotating around, that is a molecular motion as well. So it's all these types of molecular motions or atomic motion left and right that we average out. And it's all that kinetic energy summed up, divided by all the particles, that gives us an average. And that average kinetic energy then is the temperature. And so obviously we know we record this average motion with a thermometer, and that thermometer is essentially saying how many molecules are hitting the thermometer at once, and all that energy sort of averages out and moves, in the old days, mercury, up the temperature scale and lets us measure what the temperature is. Now, there are different systems of measuring this temperature. The preferred ones being Celsius and Kelvin. Those are far superior, and that's tend to be what we are using in science, whether we're chemists or physicists, or whatever. It's usually always Celsius or Kelvin. Unfortunately, we also have to discuss a third scale that some people in the world use: Fahrenheit. And between these three, this covers most of the different temperature scales you're going to see: Kelvin, Celsius, Fahrenheit. Now, water freezes at 32 Fahrenheit, 0 Celsius, 273 Kelvin. Water boils at 212 Fahrenheit, 100 Celsius, and 373 Kelvin. So Celsius is really nice because it was, well, made to be tied to water. Like, the points that it was invented for was the freezing point and the boiling point of water. So it's 0 to 100, and that's easy to remember. Look at Fahrenheit, 32 and 212, totally arbitrary. Kelvin also looks a bit confusing, but it is tied to an actual scientific concept known as absolute zero. In any case, these are the three different temperature scales. There are ways to convert these, and as I like to do in my classes, I usually give sort of all the formulas. These are easy formulas. Nonetheless, you usually have all the formulas on exams. It's more about you knowing how to use them and how to do the conversions. So don't get too hung up on memorizing things. Even simple formulas like this, you will be given just in the sake of having information available. I will note, important on this page, is that these use exact relationships. So what we're going to assume here is that these don't affect sig figs. Okay, so we've talked a lot about this in the previous lectures. You can go back and watch on significant figures. But if we are converting one temperature to another, which we're about to do on the next slide, I am not going to change the sig fig. So if I'm given a temperature of 33 degrees Fahrenheit, and that's 2 sig figs, my final answer when I get to Celsius or Kelvin better be 2 sig figs. Okay, so that's what I mean by exact relationships. Whatever sig figs go in here, that number of sig figs better come out here. So converting Celsius to Fahrenheit looks like this: times 1.8 plus 32, Fahrenheit to Celsius minus 32, divide by 1.8, Celsius to Kelvin, you add 273, Kelvin to Celsius, you subtract 273. And so this will allow you to get around from, temperature scale to temperature scale. If you're given Celsius, Fahrenheit, or Kelvin, you can convert between all three. So let's see that in action. Here's a straightforward one. The temperature of liquid nitrogen is negative 196 degrees Celsius. Brr, that's pretty cold. What is on the Kelvin scale? And 196 degrees Celsius, you can memorize or go back to the previous page. The formula, we add 273, so this should be 77 Kelvin. Now, as I said, this should be 3 sig figs, so I'll probably write this as 77.0 Kelvin. So again, this is converting back and forth between the two different temperature scales. We could also be asked, well, what is it in Fahrenheit, right? We could go from negative 196 degrees Celsius, and we could have to plug it into our formula, which is times 100 divided by 180. This is degrees Celsius per Fahrenheit. Sorry, it's 100 on the bottom, 180 on the top. And of course, adding 32. And in the end, we should get a number like negative 321 degrees Fahrenheit. So liquid nitrogen, right, is pretty cold, whether it's negative 196 Celsius, whether it's negative 321 Fahrenheit, whether it's 77 Kelvin. Those are all very, very cold temperatures, right? Which makes sense because nitrogen is the principal component of air all around us, and it is gas. So you really have to get it quite cold before you see it as a liquid. So that's temperature conversions. That tells us something about the average energy of all this molecular motion. Okay, so temperature is an average. We use Celsius, Fahrenheit, or Kelvin. Heat is not the same as temperature. And, you know, experts in thermodynamics will get really, really angry if you talk about heat and temperature interchangeably. They are not. Heat is a measure of the total energy. So thinking back to our, example of the air in the room all around you right now, some of the molecules are moving slow, some of the molecules are moving a little bit faster, and some of the molecules in the air around you are really zipping around the room. Temperature considers all of these, averages them out, and says the average energy is the temperature, and that's 23 degrees Celsius. Now, heat considers each of the energies and just adds them up. It's the total energy. And we use this total energy, this heat, in joules or calories. And so when we eat food, we know there's calories on a package because that's something about the total amount of energy we can get out of that food. A careful aside here, a calorie on food is actually a kilocalorie. So on the back of nutritional packaging, that is actually equal to 1,000 of the base calorie units that chemists and scientists use. But in nutrition world, the calories on the back of the package is actually a kilocalorie. It is confusing, I know. In any case, these are units of the total amount of energy we can get out of that food or get out of the air molecules or get out of a beaker of water. So here's a beaker of water. Here's a second beaker of water. They can both be at the boiling point of 100 degrees Celsius and be bubbling away. But this beaker has more heat, but the same temperature. Okay, so now hopefully you have some understanding. It's about the molecular motion, whether that is the molecules literally translating left, right, up, down, back and forth around the room, whether it is a molecule that's rotating in space. This is rotational motion, right? Like water molecules in your microwave, they get rotationally excited. They bump into other molecules and transfer their energy to the food, and the food heats up overall. Okay, so that is the amount of heat. That is rotational motion, translational motion, vibrational motion, all of it together. That is heat. We express those in joules or calories usually. If you want to take all that heat, divide it by all the particles, and calculate some average energy, that's temperature, and that's Celsius, Fahrenheit, or Kelvin. Specific heat is the last concept I briefly want to touch on in this lecture. And, the by the book definition here is the amount of heat required to raise the temperature 1 gram of substance 1 degree Celsius. And this is something kind of like density we talked about in a previous lecture, that is inherent to the material. Gold has a certain density, right? Pure gold. Gold has a certain specific heat. Here it is. And this is really important in sort of a practicality sense, right? You can think of having an oven and you turn the burner on and you can put a pan on top of this poorly drawn oven. Maybe it's a pot. There we go. And now you can stick your hand, I don't advocate this, but imagine you stick your hand on the surface of this pan and you have a really long arm as shown here, and you apparently have 7 fingers. So you are only going to be able to keep your hand on the surface of this pan for, I don't know, 10 seconds, 20 seconds maybe. And the reason is because it's probably copper or aluminum or something like that. These things with really low specific heats. And so it doesn't take much energy here from the surface of this stove to change the temperature of this aluminum or copper. Now, imagine instead, your arm is still going to be very long, but imagine instead that inside this pot, you have some water. And now what you're going to do is you're going to stick your hand inside the water. And you're going to leave it in there with your 7 fingers. And you're going to turn the stove on, and it heats up and it heats up. Now you can probably keep your hand in there for, I don't know, 3 to 4 minutes. It really takes a long time for the water to change temperature. Okay? And the reason is because it's high specific heat. It takes a lot more energy to change the temperature of that water, right? And it goes back to this understanding of, what is energy? What is a phase change? It has to do with overcoming intermolecular forces. And the hydrogen bonding in water is one of the things that makes it really require a ton of energy to change the temperature of said material. So this specific heat, again, is specific, as it suggests, to a element or to a compound. Ice is different than liquid water, is different than aluminum, is different than gold. The higher substance-specific heat, the more energy you have to give it to change the temperature. So you want your pots and pans to be something with a low specific heat, so it changes temperature quickly and cooks your food quite quickly. Water's high specific heat is one of the reasons why we have fairly stable global temperatures. The sun's radiation is bombarding it all day. The temperature slowly goes up, but when the sun's taken away, it also holds on to that energy very, very well. So specific heat is about how much heat you have to give it to change the temperature, but it's also about how quickly does it lose that molecular motion. And so it's about water's high specific heat. That is the reason that it will hold on to this energy and prevent, when the sun goes down, i.e. the round, not flat Earth, rotates, and we go into darkness for a little while, we don't plunge into negative 20 degrees Celsius and all freeze to death. So on that lovely uplifting note, that is the end of this lecture, where we talked about specific heat, temperature, heat, and temperature scales like Celsius, Kelvin, and the worst of all, Fahrenheit. So that'll do it for this lecture. See you next time.